Good morning.
Morning.
Today's topic, it's a number system. This is covering chapter 2 of the recommended text, but this doesn't follow strictly with the recommended text. And the topics or the subtopics that we're going to cover in this lecture, that includes decimal, binary, hexadecimal, and then briefly talk about octal number system, but I'm not going to go into details on that. And then conversions between number systems, and then signed binary, addition of binary numbers, and then digital codes. So the learning outcome, so the first line there is the learning outcome from your module spec. So what you expect to learn from these topics is to be able to apply arithmetic operations to digital number system. So I break it down. What I expect you to know: you'll be able to convert one number system to another, perform simple arithmetics such as addition, subtractions. So I put down there subtractions. You need to convert to signed binary, which I'm going to talk about later on in today's lecture. Okay, so before we go any further, so the number system that we familiar with is called the decimal number. Okay, so have you ever wondered why the number 12 is 12? Okay, so our number system is based on 10 symbols, okay, starting from 0 to 9. Okay, so that will be your 10 symbol, and we know it as 0, 1, 2, 3, so forth to 9. So decimal is also known as a base 10 number. So why, or what actually is 12 means? Okay, I'm sure you learned this when you're younger. So 12, you have the unit, 2 is the unit, so it associates to a 10 to the power of 0. And then the 1 is the 10th, and that associates to 10 to the power of 1. And a 12 is actually means it's 1 times 10 plus 2 times 1, and that gives you what we know as 12 in our decimal number system. Binary number, okay, so the word binary means 2. So instead of 10 symbols, you have 2 symbols or 2 states. Whereas in decimal, there is 10 symbols or 10 states. So what are the 2 symbols used in binary? So I put down here star and a moon, but of course it's not. Yeah. So, but it can be. So it means that it doesn't matter. It's just any 2 symbols can be used to represent the binary systems. Okay, so if you want to, we can use the star and the moon if you want to, but that makes reading very difficult. So what we do is we use the symbol of 1 and 0 because we're familiar with this symbol. Okay, so that is the first 2 symbols we use in the decimal number system. But in electronics, these symbols can also represent the state of switches. Okay, so it can be either an on state or an off state. Or in terms of voltage level, we can use it to represent a high voltage or a low voltage. Okay, as long as it can differentiate two different states, then we can use binary system to represent that. So similar to our base 10 number system, so instead of the base is 10, now our binary system, the base is 2. So meaning that is go from 2 to the power 0, and then the next is 2 to the power 1. Okay, so this is similar to our unit in decimal, and this is our 10th in decimal, but here is just 2. Okay, and then 2 to the power 2, 2 to the power 3, and then going upwards, okay, to the power of n, depending on the number of bits we use to represent our binary system. Okay, for a number 18 in decimal, that can be represented with one symbol, adds 2 to the power of 4. Okay, so we've got 1 there, and then 0 at 2 to the power 3, and then 0 to the power 2, and then 1 at 2 to the power 1, and then 0 at 2 to the power 0. And if you do the sum of this, if we add this up, this is going to give us 18. Okay, and that is how we represent a number 18 in decimal in terms of a binary system. Okay, so 10010 in binary is equivalent to 18 in decimal. So that is binary. Another number system is known as hexadecimal. So hexa is 16. So this case here we have 16 symbol. Okay, so 16 symbol. So it exceeds our 10 symbols that we know in decimal. Okay, so we got in our decimal 0 to 9, which is our 10 symbol. But we got 16 here. But we can't use 10 because in decimal that is 2 symbol. Okay, so we have to find something new to represent 10, 11, 12, all the way to 15. So 10 is represents as A, and then we have 11 is B, and then 12 is C, 13 is D, and then 14 E, and then 15 is F. So the symbols go from 1 to 9, and then A to F to represent all the 16 symbols in our 16 number system. Often used as a shorthand for the binary system, as each hex number can represent 4 binary bits. Okay, so again, the system works with 16 to the power 0, 16 to the power 1, and then 16 to the power of 2, and then going up further if you have more hex number. Okay, so for this number, D9A in hexadecimal, if you want to convert that into decimal, so we text D. So D is so slightly wrong. So D is actually 13. So it's easier if I change this to E. Okay, so E is 14. Okay, so 14 times 2 to the power 2, 16 to the power 2, that will be 256, and then 9 times 16 to the power 1, and then 16, and then A is 10, and 10 times 16 to the power 0, and that will be 10 times 1, and that's going to give us 3738 in decimal. Okay, you see that I keep putting the subscript there because we're dealing with different number system. So in order to differentiate them, know that this is the hexadecimal number and this is a decimal number. So we use a subscript H for hexa and then D for decimal. Because if we don't do that, 3738 is also a valid symbol for hexadecimal. Okay, so this could be H, and that will have a total different value. Okay, so to differentiate them when we're dealing with different numbering system, so it's best if you put a subscript there to differentiate them. Another way of differentiating, either using H, we can use subscript 16, and this will be subscript 10, and then binary will be subscript 2. Okay, so either way work as long as we can differentiate them. Okay, so each of these hexa number can be represented by 4 bits of binary system. So A is 10 in binary, that will be 1010, and then 9 is 1001, and then 14 is 1110. And if we combine all this, this will be the binary equivalence of our E9A. Okay, so why we said that it used as a short form for binary, because if we're going to code this binary number, that will be 12 bits here. Okay, so to write this 12 bits number, it will be quite long. So it's easier to write the equivalence in the hexadecimal. So if you write E9A, it's a lot shorter comparing to writing this 12 symbol in binary. So comparing the different number system, so we have the binary for 4 bits, going from 000 all the way to 1111, and the equivalence in decimal will be from 0 to 15, and the equivalence for hexa will be from 0 to F. Okay, so if you can remember this by heart, then you can quickly convert from one to the other. Okay, so especially converting your binary to hexadecimal, or even binary to decimal. So, but how you can convert binary to hexa? As I mentioned just now, you take 4 bits at a time, and then you convert that 4 bit into hexa. Okay, so for example, we have 13, which is 1111, 0, 1, and 13 in hexa, that will be D. And you take that 4 bits and convert straight to hexadecimal. And the reverse, if you want to convert a hexa into binary, so you take each of the hex and convert it into 4-bit binary. Okay, so the line didn't come out right. So it meant to show this is 8, this is A. So A is 1010 in binary, 8 is 1000, and then 2 is 0010, and then 1 in 4-bit will be 0001. And you can convert that number into decimal by taking each of that symbol multiplied by each of the value in terms of 16 to the 0, 16 to the 1, 16 to the 2, and then 16 to the 3. Okay, I'm not going to show you how. You can prove to yourself by doing that multiplication. So basically is 1 times 10 to the 3 plus 2 times 16 to the 2 plus 8 times 16 to the 1 plus A is 10 times 1. Okay, 16 to the 0. And that should give you 4746. Okay, so that is a quick run through about how or what are the different numbering system and how you can convert from one to the other. Okay, so I got an example here. So conversion decimal to binary. Okay, I'm not sure whether you have learned this before, but is to repeat divisions by 2 and then collects the remainder. So and show what is meant by these steps. So I have my 10. So it's a repeated division of 2, and then to collect the remainder. So if I divide this by 2, I get 5. My remainder is 0, so there's no remainder. It's divide wholly. And then if I divide by 2 again, so 5 divided by 2, so there will be 2, and we have a remainder of 1. And then if I divide that by 2 again, that gives me 1, and then there's no remainder. So if I read it up this way, that will give me 1, 0, 1, 0 in binary. Okay, so meaning is that our 10th in decimal is equals to 1, 0, 1, 0 in binary. Okay, if you want, we can test it to reverse the binary to decimal. So this will be 0 times 10 to the 0 plus 1 times 10 to the 1, and then plus 0 times 10. Sorry, my mistakes. So this should be 2. 2. This 0 times 2 to the 0, 1 times 2 to the 1, and then 0 times 2 to to 2, and then 1 times 2 to the 3. So this gives you 0 plus this gives you 2, 0, and this gives you 8. It's 10. Okay, so that's how you can convert a decimal number to binary, and this is how you convert from binary back to decimal. How about decimal to hexadecimal? So it's the same process, but now we divide by 16 instead of dividing by 2. How we can achieve the conversion? So we take our 30, we divide that by 16. So 30 divided by 16, we can get 2. No, we can get 1, and the remainder is 14. Okay, so meaning that 16 divided by 16 is 1, and you have 30, so which means that we have an 14 additional, so that cannot be divided. So that's what we call the remainder. So 16 divided by 30, that would be 1, and remaining 14 that cannot be divided. Okay, so in this case here, we have reached 1, so we don't have to divide it further. So basically, this is just 1 and 14, but in hexadecimal, the symbol for 14 is E. Okay, so this will be 1E in hexadecimal. Okay, so if we want to reverse this, we want to convert our hexadecimal back into decimal. So this will be E will be 14 times 16 to the power 0, and 1 will be 16 to the power 1. And that's basically 16 plus 14, and it gives us our 30 in decimal. Okay, I hope that's clear for those who didn't manage to get it the first time around, so that in future you're able to sort this out if you're given a different number to convert from decimal to hexadecimal. Okay, so that is a whole number. How about fractions? Okay, so if you want to convert decimal to binary for a fraction. So example here. So the methods, this method 1 is called repeated multiplications by 2. Okay, the steps is to repeat multiplications by 2 of the floating point and collects the carry until floating point becomes 0, or until the desired decimal place you require. Okay, so if it doesn't go to 0, you can carry on multiplying, but it just makes your more and more decimal place may not be necessary, because if you just need, let's say, 3 decimal place accuracy in your binary, then you should stop at 3. Okay, so how it works? let's say if we want to convert our 0.625 into fractions in binary. So we multiply it by 2. Okay, so 0.625, if you times 2, you get 1.25. Okay, so 1.25. So this is what we get if you multiply by 2. And we collect the carry. So 1 is the carry. And the remaining floating point, we multiply that by 2. Okay, so we take 0.25 times 2. Okay. So this fits here. Times 2, you get 0.5. And 0.5, the carry is 0, so nothing has no 1, so there will be 0. So we got 1 here, 0.1, and here carry is 0, so we get 0 here. And then the floating point, we multiply that again. So 0.5 times 2, that gives us 1.0. Okay, so the carry is 1, and then the floating point now becomes 0. So we stop here. So if we carry on multiplying, it will be 0, because 0 times 2, you get 0. Okay, so the conversion of 0.625 to binary, that would be 0.101. Okay, that's one method. Another method is called sum of weight. So we can, just like our whole number, so our whole number in binary go from 2 to the power 0, 2 to the power 1, 2 to the power 2, and then going up in the exponential term. For fractions, so we go from, so fractions, effectively this, if you assume that is a 0 point something number, so 0 to the power of 0, that will be 0. Okay, so this part outward is our whole number, and then this side is our fraction. So we go from, so instead going increase in power, so now the exponential is a negative, so it's 2 to the power minus 1, 2 to the power minus 2, and going further to the more negative in the exponential term. Okay, so 2 to the power minus 1, that will be 0.5. Okay, so this is actually 1 over 2, and this is equals to 1 over 4, and this is 1 over 8, and then so forth. If it's going smaller and smaller in terms of the fraction. Okay, so basically is 1 divided by 2, you get 0.5, 0.5 divided by 2, you get 0.25, and divided by 2 again, 0.125. So repeating, dividing it by 2. Okay, so the same example that we have before, 0.625. Okay, so if we minus the first exponential term, that will be 0.5, and that will be equals to 0.125. So that can be subtract. So we put a tick here. Okay, so the remaining of that, okay, 0.125. And then we try to subtract the next terms or the next symbol, 0.25. And now it's not possible. Okay, so if you subtract this, we end up with a negative number. So this is not possible. Okay, so this we put across there. And then the third one, 0.125. And then that's okay. You can subtract that. And that equals to 0. Okay, so again, I put a tick there. So this term you can subtract. This one you can't. And then it's already become 0. So we don't go any further. So the binary equivalent will be the one that has a tick, will be 1. And the one that I cross out will be 0. So it's 0.101. Okay, so this is another method of converting from a fraction decimal to a binary fraction. Okay, so two methods. One with repeated multiplications, which I find maybe is easier compared to this, which is a bit more tedious. Okay, so it's up to you which one you find it easier to convert from a fraction decimal to binary. And then for decimal to hexa, okay, so it's the same as the previous one. This one I'm just going to show you with the method one. So instead of multiplying by 2, so now we can multiply by 16 because the base is 16. Okay, so again, multiply the floating point with 16 and then collect the carry. So in this case here, let's say 0.94 times 16, we'll get 15.04. So the carry is 15. 15 in hexa, that will be F. And then the floating point, we multiply by 16 again. And that gives us 0.64. And then in this case now the carry is 0. And we have 0 here in our conversions. And then 0.64, the floating point, we multiply by 16 again. And then give us 10.24. And 10 in hexa. Okay, 10 in hexa is A. Okay, and then we got 0.24, and then we multiply by 16 again, and you can carry on that process if you want a more accurate fractions. Okay, so that's going to give us more value towards the 4th, 5th, and 6th decimal point. Okay, so so that is how you can convert decimal to hexa. Exactly the same process as binary, but instead of multiply by 2, we multiply by 16. And is equivalent valid if you want to convert this into binary. You can write this as 0. Again, each of this hexa converts to 4 bits. So this will be 1, 1, 1, 1. And this convert to 0, 0, 0, 0. And this is 1, 0, 1 in binary. And then decimal term at the back if you want to further convert it to get more accurate fractions. Okay, so converts to decimal fractions. So I think this is quite straightforward. So it's just basically multiplying with the right symbol value. Okay, so in fractions, in decimal, this is something we learned when we were young. So the one that next to the decimal point, that will be a tenth. That means it's 10 to the power of -1. And then the next one will be 100. Okay, so that will be 10 to the -2, and then 1,000, 10 to the -3. So for decimal to decimal, that is what we know. Okay, so that will be 4 times 0.1, and then 3 times 0.01, and then 5 times 0.001. And if you sum all this up, that is actually what it means by a 0.435. So for binary, again, we put the appropriate value for each of the symbol. So we have to the power 0, to the power -1, to the power -2, and so forth. So we take 1 times to the power -1, to the 0.5, and then 0 times 0.25, to the power of -2, and plus 1 times 0.125, which is to the power -3. And this gives us 0.625. So that's basically converting the binary fractions that we have previously back to decimal. Okay, so I'm not going to go through the hexadecimal because I'm sure you can deduce that from what we have shown in these two examples. So if you have a fraction in hexa, so basically it's just multiplied by 16 to the power -1 for the right positions of the decimal place. Okay, and then 16 to the power -2, 16 to the power -3, and so forth. Okay, if you're unable to deduce that, another way to do it is to convert it to binary and then convert it to decimal. Okay, so if you have a hexa fractions, if you're not sure how you can convert that to decimal, then you can convert it to binary first and then use this method to convert it to decimal. Okay, is that clear so far? Conversion from one number systems to another for whole number and fractions of numbering systems. Any questions? Okay, silence. I take it as there's no questions. Okay, another number system is Octal, which I did not talk about. I'm not going to go into details. Basically, Octal number system is base 8. Okay, so you can read this up at your own time, but everything we talk about apply to a base 8. So you just need to change the base number from 2 to 8, or from 10 to 8, or from 16 to 8. Okay, so everything is applicable. The only thing is binary to octal. So hex to binary is 4 bits at a time. And then oct to binary is 3 bits at a time. Okay, because we know that to the power of 3 is equals to 8 to the power of 1. Okay, so we can represent 3 bits of binary in one octal number. And then the symbol is going from 0 to 7. So it means that the octal number system, we cannot have, so no symbol, no 8 and 9. Okay, so we don't have 8 or 9 in our octal number system. It's only count up to 7. Okay, so negative number, I think I should go back to this slide later. Okay, so for a 16-bit number, we can represent negative number. So not just 16 bits, but we can use binary number to represent a negative number. And how we do that? Using a system known complements. Okay, so we take an example. So here on the top, they show you that plus 3, this is my binary number in 16 bits. And then minus 3, this is my binary number in 16 bits. And the equivalent of that in hexa. So obviously, if you convert this binary into hexa, this will be 3. And if you convert this to hexa, you take 4 bits at a time. So this will be F16, not 15. Okay, and then F, which is 15. And then this will be D, which is 12, not 13. Okay. So this is the equivalent of a minus 3 in this numbering systems that allows negative number. And what is actually meant, or how we can get from a positive 3 to negative 3, we use a system called a 2 complements. Okay, what is a 2 complements? So the first complement, or 1 complement, is when we invert all the bits. Okay, so for example, start off with 3 in 16 bits, we have all this 0 and then 1, 1. So invert every bit, which means that when it is 1, we make it 0. Okay, so we invert all the bits, 1 becomes 0, 0 become 1. Okay, so this is known as the first complement. The second complement, or the 2 complements, is when we add 1 to the first complement. Okay, so we plus 1 to the inverted bit. And now we get this number here at the bottom. And this is known as our 2 complements of the positive 3 number. So we start off with positive 3, or positive number. We invert all the bits, and that's our 1 complement, or the first complement. And then plus 1, and we end up with our 2 complements. And that will be our negative 3, which is the number here. So positive binary can be converted to negative binary by performing a 2 complements. Okay, so here's an example or an exercise. So generate in binary and hexa the negative number for -1, -5, -8, -10, and -1 to 8. So now, for this lecture, maybe you want to try -1 and -10. Okay, so for 8 bits, so we start off with a positive 1. So we got 0, 0, 0, 0, 0, 0, 0, 1. Okay, so 8 bits. So 1 in binary, it will be 1. So we fill up the rest with 0 to fulfill our 8 bits binary. So the first complement, we invert all the bits. So 1 becomes 0. And then should be here. Okay, so invert all the bits. That is our 1 complement of the first complement. And then we add 1 to that. So we got 4 ones here, and then 3 1 and 0. And then we add 1. So we end up with 8 ones. The result here, which is our 2 complements. And it is our -1. In hexa, we can convert this every 4 bits. So 4 ones is 15. 15 in hexa will be the symbol F. So this will be FF. Okay, so positive, a -1 in 2 complements representations. That will be, we start off with a positive 1, inverts every bit, add 1, and that gives us our -1 in binary. Okay, so try again for -10. Okay, so So 8 bits for 10 is 1, 0, 1, 0. Okay, I think you are correct. My answer is wrong. Okay, so we invert all the bits. So 0 to become 1, and then we add 1. So if we add 1, this should be 0. So you got the right answer. Okay, so I presume you now understood how to convert a negative number using the 2 complement system. Okay, so going back to my initial slides. Okay, so what we show is that negative number, so the 8 bit is what we call the sign bit. Okay, so 8 bits, in this case, on an 8 bit system, the 8 bit show that the sign of the binary. So if it's 1, it's a negative number. If it's 0, it's a positive number. Only the 7 bit is used to for the number. Okay, so and the number systems going for the positive one will be the normal binary, and then for the negative number is from the 2 complements. Again, from the negative number, if you want to work out, convert that into positive, again, you can do 2 complements to that. Okay, so that is our signed binary number used to represent positive and negative number. Additions of binary number, so it's the same as how we do normal additions. It's just that we only have 2 symbols, 0 and 1. So in decimal, if I add, let's say, 9 and 2, okay, so this 9 is the maximum in our symbol in decimal. So what we end up with, so we add 2, we know that this is 11, so the unit is 1, and then we have 1 carry over to the next, to the 10th, to the unit 10. Okay, so this will be 11. So the same thing for binary addition. So here it's quite simple. So 0 plus 1 is 1, 0 plus 1 is 1, and so forth. The second case, so 1 plus 1. In our decimal, we know 1 plus 1 is 2. But in binary, you don't have the symbol 2. Okay, so for 1 plus 1, that will be 0, and 1 carry over. That is 1, 0. Okay, so we get 1 carry bit. And then 1 plus 0, we have to add the carry bit as well. Just like here, if I add, let's say, with 12, then this will be 1 plus 1, this will be 2. Okay, so here, so we have 1 plus 0, we have to add the carry as well. So again, 1 plus 1 is 1, 0, and then we got 0, and then carry 1 bit, and then we go on with our additions. Okay, so this is binary additions. So no different from the decimal, except that when it exceeds 1, so it means that if you add up to 2 and above, then we have a carry. Okay, so I'm not going to go into this. This will be repeated when we're doing adder circuits later on. Okay, so it's to show you how we do additions using logic circuits later on. Okay, subtraction. So in our digital circuits, we actually can't do subtraction. Okay, so digital circuit can only do addition. But in order to achieve subtraction, so what we do is we use a signed binary number. That's what we talked about just now. the two complements. So for example, if you want to subtract 5, you have to convert 5 to -5, then do additions. Okay, so what it means is that, let's say I want to do in decimal, so is 10, I want to do -5. So because our digital circuits can't do subtractions, so we have to do 10 plus -5. Okay, so we have to convert 5 to negative and then do the addition. So this is the addition operations. So we have to convert all this into signed binary number. That's where the two complements come into play. Okay, so okay, so that is dealt with addition and subtractions. So that covers most of the parts of our numbering system. The next part is about different systems. So this is not so much about numbering. This is more of a code. So this is called binary coded decimal. Okay, so this is not the actual number system, but in actual fact, it's a code. So meaning that if you have our decimal, we're going to represent all our 10 symbols in decimal in a 4-bit binary code. Okay, so the easiest way or the intuitive way to do this is to code every symbol of our decimal with the equivalent binary number. But in the 4 bits, our binary number can go up to 15. So it means that we're going to discard the binary number for 10, 11, 12, 13, 14, and 15. So all this code for 10, 11, 12, 13, and 14, and 15 are all invalid binary coded decimal. Okay, so we're going to make every number or every symbol in decimal into equivalent 4-bit binary. And the application of this is for what we know as a 7-segment display LED. Okay, so this is a 7-segment. So we have 7 LED lights to form a number. Okay, so this is commonly used in your calculator. Okay, so your calculator number is represented using this 7-segment display. And the binary coded decimal is used to convert the decimal to light up this 7-segment accordingly. Okay, so for example, if a 0, we have a VCD code of 000, and that will signal the 7-segment to light up A, B, C, D, E, and F to display number 0, for example. Okay, so to convert decimal to or from a binary coded decimal, so we take each decimal number and convert it to a 4-bit binary number. Okay, so example here, we convert 2469 to BCD, binary coded decimal. Okay, so basically you take every digit of the decimal and you convert it into 4-bit binary. So instead of the normal conversions using the normal binary number, we now just convert straight from the decimal number into 4 bits and combine them. Okay, so 9 is 1001, 6 is 0110, 4 is 0100, and 2 is 0010. And that will be our binary coded decimal. And the reverse, so we just break up the bit or the code into every 4 bits, similar to what we do in converting to hexadecimal, except that here we don't have the code of 10 and higher of the binary. Okay, so we shouldn't have A, B, C, D, E, and F. If you have that, which means that something is wrong with your BCD code. Okay, so there is conversion from decimal to binary coded decimal to and from. Okay, addition. So because we have a range of value that is invalid, so we do our normal binary additions, 4 bits. We look at every 4 bits of the results. If that 4 bits is greater than 9, and then we're going to add 6 to that. So for example here, so we have one BCD code, add another BCD code, and here, so we look at every 4 bits. Okay, of additions. So here we have 11th. So 11th is greater than 9. So we're going to add 6 to that. So we're adding 6, which is 0110 to that 4 bits. Similarly, the second 4-bit addition is add up to be, again, to 5 bits. It's more than 9 as well. Okay, so we're going to add 6 to that as well. Okay, and then we do our normal binary additions, and that gives us 1100000001. Okay, in terms of again, we can convert that back to our decimal. So this is binary coded decimal. So this is the sum. Okay, so if you want to know what is this in decimal, again, we can convert that back to decimal by taking 4 bits at a time and convert that into decimal. So here 0001 is 1 in decimal, and 1000 there's 8, and then 1 is 1. Okay, so we can test this out. So this is We can convert this into decimal. So here will be 9, 1, 0, 0, 1. 0, 1, 0, 1 is 5, so it's 95. And this is 1, 0, 0, 0, that's 8. 0, 1, 1, 6, no, 0, 1, 1, 0, this will be 6. So we are actually adding 95 with 86. So our normal decimal additions that give us 181. And that's tied up with our binary coded decimal as the sum. Okay? So that is how you can do additions of binary coded decimal. Okay, so the steps is up here. So we add 4 bits at a time, and if the result is greater than 9, we're going to add 6 to that result. Okay, so other digital code that are used in digital systems, one of them is called gray code, and the other one is called alphanumeric code. The standard one that is called an ASCII code. Okay, American Standard Code for Information Exchange. And another one is called Unicode. Okay, so these are the two commonly used code in your computer system. So we're going to look at what is gray code. So this is not arithmetic code. Okay, so is you can't assign a value to them actually. But what gray code is that it has to ensure that there's only one bit change between adjacent code words. Okay, so which means that in our decimal 0, our binary is 0, 0, 0. And if we start that off the same code for our gray code, and then we have 1, so we code that with 0, 0, 0, 1. So meaning that from here to here, there's only one bit that changed. And that's to the next code. In a binary for 2, we have 0, 0, 1, 0. And this violates our gray code, because in this case, in our binary, so we have 1 becomes 0, and then 0 becomes 1. So we have 2 bits changes from our binary 1 to 2. But in gray code, we want to maintain only 1 bit change at a time. Okay, so in this case here, we're going to make this bit change, and then we keep this bit. Okay, so the less significant bit is kept, so it becomes 0, 0, 1, 1. And then to maintain that, to go to the next state, again, we only want to change 1 bit. So this is the bits that change. Okay, so you can see that from each of the state is only 1 bit changing. Okay, so I'll let you identify them as you go down to the list of the different states. So the gray code is to maintain that from one state to another is only 1 bit changing at a time. And to convert the binary to a gray code, so we take the most significant bit. Okay, so this is what we call the most significant bit, and this is in binary, we refer this as the least significant bit. Okay, so this has the smallest value, and this has the highest value. So to convert binary to gray code, so the most significant bit is the same, so we kept the most significant bit. Okay, so 1 maintained at 1. And then we go from left to right at each adjacent pair of the binary and to produce our gray code. Okay, so we sum this, and that gives us 1. And then we carry on, and then we sum this, and this gives us, so 0 plus 1 gives us 1. And we carry on down until we reach the least significant bit. So 1 plus 1, that will be 1, 0. We discard the carries. So 1, so here add up to be 1, 0. So we discard the carry. So we have 1 here. No, we have 0 here. And then the last pair be 1, 0. So 1 plus 0 gives us 1. So this will be the equivalence of this binary number in gray code. Okay, so this is converting from binary to gray. Then the reverse, okay, from gray code, again, the most significant bit is kept. So this bit here, same. Okay, so and then we take this bit plus the next bit, and that gives us our binary. Okay, so meaning that here we sum it this way, and that gives us our binary code. And then we repeat that. And then that gives us this. And then go down the list until you reach the least significant bit. Again, the same thing, we're going to discard if there is a carry. Okay, so that's converting from gray code to binary. Application of that, this is one of the applications why we want to change 1 bit at a time, is to prevent error. Okay, so consider this. This is a decoder trying to decode a spinning disk with a coded binary. So if the coded bit is using the normal binary system, so it's going from 0, 1, 2, 3. So here it's changing more than 1 bit at a time. So consider when this disk is spinning, okay, when it reaches this position, let's say going from 1, 1, 1, 1 to 0, 0, 0. Okay, so let's say this position is spin all the way to here to the detector. If there is misalignment of this detector, okay, so this detector trying to detect the 3 sector of the disk. So if, let's say, this tree detector is misaligned, we have it, let's say, from here originally, and then when the distance is slightly misaligned, it's go from this. Okay, so something like that, misalignment. So it's going from 111 to 110 before it gets to 000. So this is an error occur, or even it might even go to 100 before it goes to 00. Okay, so because of this way of coding, you have more than one bit changes. So you have two invalid states transition from 111 to 000. But if you use a gray code here, that will never happen. Okay, so if it's misaligned, it will be like that, for example. So it will still read 101. Or if you are here, if it's misaligned, it will still staying at the previous state until it gets to 000. Okay, so this prevented this sort of error from occurring in the gray code. Okay, so that is one of the applications of the gray code. This is just a table of the ASCII code. I don't expect you to remember this, so it's just to be aware that these are how binary are coded for different symbols on your computer mostly. Okay, so with that, I will end this lecture. This cover all the bits that you require to know for the numbering system for this module.